All right, today we're tackling the constant speed paradox. And it's a real head scratcher, something that seems to, completely break the rules of common sense. But here's the crazy part. This isn't some abstract physics problem. It's happening literally all around you all the time.
So here's the big question. How can something be accelerating if its speed isn't changing at all? I mean, we're all taught in school that acceleration is just, speeding up or slowing down, right? Well, it turns out that's only half the story. And the other half, well, that's what we're digging into.
Just think about it. You've got the tip of a propeller on a plane, just spinning at a constant rate. Or what about the second hand on your watch, just sweeping around and around? Even a car rounding a bend holding a steady 30 miles per hour. Or a satellite in a perfect stable orbit around the Earth. In every single one of these examples, the speed is constant. But trust me on this, they are all accelerating.
Okay, so how is that possible? Well, the key to unlocking this whole paradox comes down to one really important distinction: the difference between speed and velocity. Now, I know they sound like the same thing, but in the world of physics, they are worlds apart. And a difference is actually pretty simple when you break it down. Speed, that's just a number. It's a scalar. It just tells you how fast you're going, like 60 miles per hour. That's it. But velocity? Velocity is a vector. It tells you how fast you're going and in what direction. So 60 miles per hour north. And this right here, this is the whole game. If you change your direction, even if your speedometer doesn't budge, you have officially changed your velocity.
And here's where it all clicks into place. See, acceleration, by definition, is any change in velocity. So if you change your direction, you're changing your velocity, which means you're accelerating. It's that simple. As our source material points out, even if the speed is a constant, a particle can have acceleration if it moves along a curved trajectory such as a circle. The second you start to turn, you are accelerating, period.
Okay, so this special kind of acceleration, the one you get just by moving in a circle at a constant speed, it's got a name. And that name is centripetal acceleration. Centripetal acceleration is basically the thing that forces an object to follow a curved path instead of flying off in a straight line. And the most important part to remember is its direction. It's always pointed directly toward the center of the circle. It's like an invisible rope, constantly pulling the object inward, keeping it on that circular track.
The name itself is a fantastic clue. Centripetal comes from the Latin words for center and to seek, so it's literally center-seeking acceleration. I think that's awesome because it's so perfectly descriptive. It's not about going faster or slower. It's an acceleration that is always seeking the center of that circle. And believe it or not, the math for this is surprisingly elegant. Centripetal acceleration, we'll call it a sub c, is just the speed, or v, squared, divided by the radius of the circle, r. And that formula tells you something that you probably already feel in your gut, right? The faster you go, or the tighter that turn is, the more of that center-seeking acceleration you're going to need to make it. And check this out. This just shows you the insane range of this one concept. I mean, look at these numbers. The moon, as it goes around the Earth, has this tiny centripetal acceleration. Then you jump to a fighter jet pulling a few Gs in a barrel roll. That's a lot more. A roller coaster can be even higher. But then, look at an electron inside an atom. The acceleration is just mind-bogglingly huge. It's the exact same physics from the moon down to an electron. That's just wild. All right, so we've pretty much cracked the paradox for perfect, steady, circular motion. But let's be real, the world isn't always that clean and simple. So what happens when something is moving in a circle and it's also speeding up or slowing down? Let's put you back in that car, right? You're going around the corner, but this time you're not just cruising. You're stomping on the gas pedal. So now you've got two things going on at the exact same time. You're changing your direction and you're changing your speed. Well, this messy, real-world scenario has a name too. It's called non-uniform circular motion. And to really get a handle on it, we need to introduce a second kind of acceleration. And this one is called tangential acceleration. It's pretty straightforward. While centripetal acceleration is busy changing your direction, tangential acceleration is what changes your speed. Its direction is tangent to the circle. Think of it as pushing you forward to speed you up or pulling you back to slow you down. So now we have these two players on the field at the same time. Two different accelerations acting on one object. Let's put it all together and see what the whole picture looks like. As our source material puts it so well, the total acceleration is simply the vector sum of both parts, the centripetal and the tangential. Now, vector sum sounds complicated, but it just means you're combining the two effects. You've got one pull toward the center, changing your direction, and another push along the curve, changing your speed. The total acceleration you actually experience is just those two things working together.
So let's break it down one last time. Step 1, U-turn. That means you automatically have centripetal acceleration, pulling you toward the center and changing your direction. Step 2, you hit the gas or the brakes while you're turning. Now you've added tangential acceleration, which changes your speed. And step 3, the total acceleration you feel is just both of those combined. That's the whole shebang.
So what are the big takeaways here? First, and most important, acceleration is any change in velocity, which means speed or direction. Second, just moving in a circle, even at a constant speed, is a form of acceleration. That's our centripetal friend. And finally, if you decide to change your speed while you're turning, you're adding a second tangential acceleration to the mix. The total acceleration is just the combination of both.
But that leaves us with one last really big question, doesn't it? This center-seeking acceleration, it can't just happen on its own. Accelerations don't just pop out of thin air. Something has to be causing it. So what is the force that's actually doing the pulling? What's the force that's pulling on that jet, that planet, or you in that roller coaster and yanking it toward the center? Well, that's a whole other can of worms and a story for another explainer.